here we go. Here is my joke. It is so terrible. I found this like on the internet, and there, like with just the aesthetics of it, there is something just so like the Y2K bug was never solved by it. But anyway, that's my that's the thing that I'm going to add. So there you go. We're gonna make some bears out of datas. Okie dokie. So without further ado, this is how did this talk come about? I needed to do a talk because I couldn't get off my ass to get a good talk organized. So I thought, hey, it's been a while, I should do a talk. But I've been sort of collecting these little things, like sort of gems that aren't big enough to have their own talk. And so I've never really done a talk about them, but they've just kind of like built up over the years. And so that's why I kind of titled this Cleaning Out the Closet at the Back of My Mind Palace, because it's kind of like these little things that I squirreled away in a shoebox, which are like kind of cool, but each one is not big enough as its own talk. So I've kind of just like broken it up. So you're going to get like 4 or 5 different kind of like little vignettes. And, you know, this is, I really want this to be 2 ways. So please ask questions, and hopefully I can like access the chat while, no, I can't see the chat while I'm screen sharing. That's really annoying. Oh, well, anyway, maybe I'll just try and flick back and forth or something. So subjectivism is correct, objectively correct equals 1. So one of the things that I think about a lot, strangely enough, is that what is a probability? And if you've never asked yourself this question before, as soon as you do, you start running down some pretty weird rabbit holes. So I'll give you an example. If the kind of sort of high school thing you get told is like, I'm flipping a coin, and if I flipped the coin infinity times, it would come up heads like half of them or a quarter of them or whatever it is, and that's the probability. Some people call this concept like frequentism because it's like the frequency of something happening, but you know, that's just sort of this notion that it's like you do something infinity times. Now there's sort of a big problem with that, which is that that doesn't make any sense at all for something that you can't do again. So for example, like a coin, at least I can sort of imagine how I'd do that over and over again, but something like, you know, Donald Trump versus Joe Biden, it's like, we can't have a do-over. We can't just be like, okay, reset the world, reset America, run the election again. It just doesn't, it doesn't really feel like it has a lot of coherent sense. So there is one other interpretation of probability, which is called subjectivism. And that's the notion that the number between 0 and 1 really just represents a degree of belief. And what that degree of belief means is kind of up to you, so long as the only thing that makes it a probability is the fact that it shares certain rules and certain kind of like coherencies. Maybe I'll just, you know what, this is one slide. I've got a whole slide for this, one slide for this whole section. So I think I can like stop sharing while I talk. So, when you, this also makes it a lot more kind of, I think the word would be like sensical and coherent when you deal with things like regression. Because when you think about it, like if you're measuring a real quantity with like whether the coin comes up heads or tails, that is this ground thing which you can in principle even measure. But so then replication kind of makes sense. But let's just say I'm doing sort of a regression and I have this thing that I call like someone's propensity to vote liberal or vote Labor. Now that's just a number. Maybe it's a number, maybe it's 10, maybe it's 4. It doesn't really matter. But the point is I can't go and physically measure that. I can't like get a drill and like drill into someone's head and be like, aha, I found the bit of your brain that makes you want to vote Labor or liberal or whatever. So in that sense, then when I do my kind of probabilistic inference and I get some sort of distribution over, say, you know, probability of voting Labor, that is just a degree of belief. It's subjective. It just says, you know, when I believe something 0.4, it's twice as much as believing it 0.2. And I don't really need to try and over-interpret it too much. And I think this is a really important point because it makes probabilities, and especially like what you are doing with inference, a lot less confusing, because now what you're doing is you're just saying, I am going to look at the evidence and figure out how I should update how I think and what I believe. And I don't have to then get confused about what I believe's connection necessarily to like the ground real world. And I'll give a concrete example of that, which is that often if two variables are independent, they're kind of in folk epistemology or like folk probability treated as there's no causal link between them. But this is like totally wacky because like I could just have a model where, you know, I have a normal distribution and I have a distribution then, like I do a Bayesian inference where my correlation coefficient has, you know, can be 0 or can be something else. So as I'm doing inference, I'm also learning whether these two variables are independent or not. And so in that sense, based on evidence, these things could be independent or not independent. But in the world, one caused the other or it didn't forever. It's kind of the same problem as if I am in the dark and I see this shape, it has 4 legs, and I go, I'm 50% sure that's a cat and 50% sure that's a dog. It's not half a dog and half a cat. It's just my subjective state of knowing what this thing is indeterminate. So in that way, probabilities, I think, become a lot easier to understand and think about once you accept that they're simply like a kind of quantification of an internal subjective judgment. But that being said, another more technical reason to like accept subjectivity is that if you are a subjectivist and you are to some extent rational, i.e. if I tell you that if I flip this coin infinity times, half the time it'll come up heads, then you have a very strong sort of, what's the word for it, incentive, a very strong reason for then assigning the belief level 0.5 to the statement, this coin will come up heads. So in some sense, if you take subjectivism plus rationality, you end up with something like frequentism in the cases where something can be in principle replicated. So that's just something to think about. I'm gonna keep moving unless people have like questions about that. Oh, thanks Jen for putting out that link. Yeah, questions? No? Jack, how you feeling? You wanna ask some questions?
I would say that in this case, frequentism is the belief that the coin is fair and you're telling the truth. I don't say this as a joke. Frequentism means believing that the coin is fair and you are telling the truth. Still, unless I've done, if not an infinity time of throws, at least a long enough number of throws, I can't assign any probability but based on belief.
Yeah, I think maybe I don't want to get like too bogged down in like people use frequentism in slightly different terms and contexts to mean slightly different things. But I think the more important thing is that whether the probability of heads is a property of the coin or simply a subjective kind of judgment that is you-centric. So is it the probability of something that belongs to the coin, or is the probability something that belongs to you? I'd simply say that subjectivism is kind of, I'm pushing towards the notion that it belongs to you. There's nothing about the coin that really matters in that case. Awesome. Thank you, Javier. Okay, cool. Next thing. This is, and like all apologies to people who, hang out with me because I've been slack about letting people in. All apologies to people who hang out with me because they've heard like half these rants before, possibly several times. So, and my partner just joined the chat as I said that, so I am sorry. There is no such thing as prediction. So this is, I'll go back to screen sharing. Can I do just there we go, share. There's no such thing as prediction. And this sounds crazy, but what do I mean by this? There is never a situation where you go and collect a lot of data and spend a whole bunch of money doing it, build a model, and then just ignore the results. So this is one thing to keep in mind is that, and this, I guess, relates to many different areas of machine learning and AI, but always keep in mind that people want to use predictions to do things. the thing that, or more importantly, no model is really a predictive model. It's just that you have a kind of logical algorithmic front end to some decision-making process. And these things are going to be much more clear if you kind of keep them end to end, as in we are trying to make a decision on data, and we always going to act on, we'll go try and act on information we have. And that's why, say things like understanding how the decision that a model makes is going to be used can be often as important or more important than where the data came from, how accurate it is. It also means that if you are sort of in the research field, any time you try and build a predictive model, if no one ever used that prediction, or people took your predictive model and were like, oh, hey, it's accurate, and then just left it there and didn't do anything, that would be a failure for you. So in some sense, succeeding is getting people to do things with your predictions. And you should always be kind of like very careful about that, because I think there are some high profile cases where, you know, people have tried to predict various things about people from their voices or pictures of their faces. And eventually those, the concern has always been that if you, how do I put this? If you are going to, you know, try and say something about someone from like a picture of their face, then downstream decisions will be made from that. So there's this kind of idea that there's always a causal link. Once you do modeling, there's going to be always a causal link between data and what you personally or your organization is doing. And that's something that's, I think, often overlooked as thinking that a prediction is kind of passive. So I would say that's something to always keep in mind and be careful of. Laura's laughing.
I mean, Andy, would you say that applies to like all types of predictions, or just predictions based around people and their behaviors or what they might do in the future? I mean, you can say that there's no such thing as a pure kind of prediction, but what about something like a model that predicts the temperature tomorrow, or something like that?
Yeah, I think that's a super good question. So I mean, in my mind, you know, if we're trying to predict a stock price, right? Like that on its own is not useful. What I want to do is buy and sell. If I'm trying to predict the weather tomorrow, I'm going to have some downstream use of that. I'm going to try and publish it and maybe charge a subscription fee, or I'm going to try and, for example, use it to like plan my picnic or whatever it is. But my point is simply that there is almost never a situation, like never a consequential situation where we make a prediction and then just ignore it. We act on predictions. And like as a professional, like outside of just the ethical concerns, as a professional, you'll be able to provide kind of the most value to, say, you know, your business or your customers if you have a serious think about like, what is it that I actually am going to use this for? Like, for example, even if I'm predicting what movies people will like, I want to recommend them and eventually get people to watch them more. So that's, again, still an act, not a sort of a prediction. And it's obviously predictions are a thing. It's just a turn of phrase, you know. But awesome question. Thanks, Jack.
I can just to draw your attention to it. I can see Lizzie has asked a similar question in a much more intelligent way. If you comments there.
Yeah, the key difference seems to be whether your action is affecting the system that you're trying to predict or not. If it doesn't affect that system, you can treat it as a pure prediction. If it does affect that same system that you're predicting, then you have to treat it as an intervention.
Yeah, I think that's a really, really great observation, Lizzie, which is that, like, I think in the extreme, we can come up with situations where your predictions will really have, like in the case of like a rocket trajectory and like Mars's orbital path, that really is a situation where there's like the effect is so negligible as to be unimportant. But I think that in the real world, there are surprisingly few of those. Anytime you, for example, assess credit risk, you're then assessing who's getting loans, which then affects their future credit risk. If you're recommending movies, you're affecting what people are exposed to, and you could even be like changing their tastes. So I think that there is very, very few, like surprisingly few real world situations where when you act on predictions, that won't feed back somehow. And I think that, you know, in the academic world, it's pretty easy to sort of say, well, you know, like my predictions aren't going to affect like this data set because that's the scope of this paper. But often that scoping is a lot broader when, I guess, like economics becomes involved. Is that a useful answer, Lizzie?
Yeah, although I think the time it takes for things to feed back is relevant. Like maybe my intervention changes the system, but that flow-on effect just sort of isn't relevant for the next 3 years or something, and so I can treat it as a prediction now.
Yeah, absolutely. And I would say that like making a positive decision to be like, from our analysis of how this is going to be used, we can safely say, or at least in our judgment, we can say that this will be at, you know, timescales of a year or 2 years more of a prediction. I think that sort of makes sense. But to even make that, you need to take into account what interventions you're thinking of doing. So I would say like you know, there's no such thing as prediction is trying to say, well, if you scope it and you say, okay, this is going to be a pure prediction on the course of, say, you know, one month or something, that might be where you can kind of try and like reduce the scope down to an area where you can feel like it's reasonably stable. But I would say that if you actually take a sober look at that, the scope where you can say that this is going to be a pure prediction is often like surprisingly small.
But predictions are much easier figuring out what to do with interventions.
Yeah.
So that's probably why people do it. Not because it's correct, but because it's easy.
Yeah, absolutely. But luckily in this next section, we'll be talking about something that's very easy. So thank you for that lovely, lovely segue. So I'm going to, here we go. I've done a little bit of marketing on this one. So here we go. Share. So this is all from the first, I think, 2 chapters, chapter 2 or 3 of E.T. James's book, Logic of Science, Probability Logic of Science. So if you haven't got this book before, I highly recommend at least leafing through it because it's a classic. But so I'm going to talk about Bayesian ABS. So this is ABS in 2 minutes, where ABS is a Bayesian system. So this idea all started when I read about this decision-making system which Benjamin Franklin proposed. So he apparently wrote like this monograph to his descendants, which was basically his kind of like advice to them. And this was one of the things in it. And it was very, very simple. You want to make a decision between 2 things. Well, you make 2 columns like on a piece of paper, and you have 1 column for positive arguments and 1 column for, well, arguments for one side. The other column is arguments for the other side, and you write them all down. And then he said, basically, cross off arguments from one side or the other. So, you know, a weak argument on one side could eliminate 1 weak argument on the other. And I'll start drawing this just so we don't get sort of confused. So here we go. Screen share my whole desktop, and now we should be able to see the Jamboard. Yeah, how's the thing? So we're gonna draw 2 columns, and we're gonna write, you know, new car and no new car. And so I might say, okay, I want to, you know, new car smell. And then I might say expensive. And then I might say something like, I don't know, get to work faster. I don't, it's a faster car, okay? And then I might say, okay, well, this one cancels out this one. So his basic idea was write down arguments on each side, and then you can sort of cross off some. And he said, if you have a particularly strong argument, like for example, I don't know, like new sound system. Maybe you really love music. Then you might be able to cross off two arguments. Old car is good enough. You might be able to cross out two arguments on the other side for one argument on this side. So here I've crossed out two arguments there. It's just saying that, okay, you can have a rough idea of the strength of an argument by which ones you cross out. So I'm going to propose that, and this is kind of like a little interesting conjecture, but I would say that most structured decision-making systems have a Bayesian interpretation. Why is that? Well, it's just because if you are trying to be clever and you're trying to be consistent in how you make decisions, there will be like a little nugget or fragment of Bayesianism in there. So I'll give you an example. Here is the Andy's a Bayesian system in action. So this is like a little simple thing. I wanted to keep it topical. So we've got, I have COVID and I don't have COVID. So here we go. Here's some evidence. I have a cough and I'm going to write 3 points. And I have a fever and I'm going to say, okay, that's 3 points too. And I've got shortness of breath. I'm going to say, that's pretty bad. That's 10 points. And then I'm going to say, okay, well, I've been doing social distancing. That's 6 points against. I've been wearing a mask in public. That's 3 points against. And now, very importantly, I've added a prior as well. So here I've put the prior of 40 points, and we'll soon see why like that prior makes sense. But you can see that I have put that down. So what have I put down? I've put down what my hypothesis space is. I've put down what my prior is, and I've put down points for each different piece of evidence I have. And then finally, I can add up all my points, and then I can look at the difference of points that's remaining. And so if I wanted to make a decision, sorry, that should be 7 over there. I did these slides quickly, but that should be 7 here. Just ignore that. So then I might make the decision that, yeah, I have COVID, given especially the weight of the evidence of the COVID test, which is a full 30 points. So this also has the property that you can fairly confidently cross out things. So for example, like social distancing could cross out cough and fever, or mask in public plus social distancing could cross out shortness of breath. So this is kind of like this 1 or 2 arguments kind of canceling out each other. But now here's the magic bit. If I told you that this is fully Bayesian, and this is what's interesting about this is you could do this without any with basic primary school mathematics. You could explain this to like a child and they could use it to make decisions and probably be making decisions better than most statisticians. So here goes. Those points are log odds on a decibel scale. And so I'm going to claim that the decibel scale is absolutely the best possible way you can measure evidence. So here goes. There's this sort of thing where when I first came to like log odds, it was really freaking confusing. So I'm going to explain, this is like log odds, super simply explained. So here we go. Here is my table. I've got odds of 1 to 1. So 50-50. So this is my odds, my probability, and my decibels. So that's 0 decibels. What's freaking magic about decibels is that whole numbers of decibels, for example, 3 decibels, corresponds to a nice whole number ratio, very, very, very closely. So this is approximate, but very close, corresponds to a whole number ratio and a whole number probability. So we can say like 3 decibels is, for example, a 2 to 1, 6 decibels is a 4 to 1, 7 is a 5 to 1, and 9 and 10, 8 and 10 to 1. And you can see that as we add here, we basically sort of multiply here and we move along here in this like nice nonlinear fashion. And if you recognize on this side, that is going to be the same shape as like a sigmoid curve, but with a specific scale. And this is why we use this decibel scale. Is there, how have I done? It's hard to get feedback on like Zoom, so I'm going to go off screen sharing and see if we've got questions. No? Okay. Well, someone with a mic, feel free to like butt in and tell me to explain more.
Or if you're more comfortable, you know, chuck in your question in the chat and I'll read it out.
Cool. So I will go back to screen sharing. So what is super surprising about this whole setup is just the fact basically that we get so many useful ways to put together evidence in intuitive ways. So if I, for example, if I can do a pretty good job of figuring out like, you know, is this, you know, a sort of like a 50-50? Is this, am I pretty confident about it? You can see that in some sense, these numbers fairly well correspond to our notion of like weak, moderate, and strong evidence. So 3 dB here is corresponding to a 2-to-1. So that's like, yeah, on balance, I think that's more likely, but not that much. 6 corresponds to, okay, I'm becoming more confident. 10 is corresponding to, oh yeah, like I'm 90% confident. And another way to think about it is that 10 dB of evidence is the amount of evidence you would need to take you from a priori being totally indifferent to being 90% confident that this is the right decision or that this is the correct hypothesis or this is the true hypothesis. So in some sense, like going back to subjectivism, this table here gives us a way to kind of like match up intuitive notions of weak, moderate, and strong argument or evidence into a way that we can reason about and in fact use very, very easily. Now, the other beautiful thing about evidence on the decibel scale and logit scales in general, sorry, is the beautiful symmetry within them. So you can see here, as I go positive decibels, we have ratios that are, again, nice whole numbers. But as I go to negative, what we get is just, in this column, we flip the odds around. So for example, 6 dB is 4-to-1, negative 6 dB is 1-to-4. Not only that, this column here is 1 minus whatever the negative one is. So for example, negative 6 dB is 1/5, and here it's 4/5, or negative 10 dB is a 10% versus plus 10 dB, which is a 90%. So they're kind of symmetric in that way, in that this column goes negative or positive, this column flips around the colon, and this column is 1 minus the counterpart. And I have a slide somewhere about that. Oh yeah, so this is kind of one way to put that. So we have 0 dB is 1-to-1 and 1/2, and then we can see kind of like negative and positive evidence as having this nice kind of beautiful symmetric structure around odds and around probabilities. And that justifies just adding them up in this step. And so I'll show you how we do that. So what we'd really like is an additive Bayes rule. So this is like a nice little tight notation for an additive Bayes rule. We're going to say the evidence, which is in this case the decibel log odds of a hypothesis given data, is just equal to our prior odds plus this EH. And this is the really important thing. This is the evidence for hypothesis H given data D. And if you make these substitutions and then you simplify, you will get this additive Bayes rule. And one important thing to look at this is not a proportional here. This is exact. So in the case of independent evidence, we can simply add it all up and continue to update our posterior by just adding this evidence from this scale here. So I'm really interested in being able to use this to say, like, teach either children to reason or teach people who don't want to do complex mathematics, or even if you just want to use this kind of in everyday, you use this every day, you can't use Bayes' rule because it's too difficult, because you can't multiply all these like fiddly fractions in your head. But by doing this decibel log odd scale, you can. So how the hell do we get these sort of evidence numbers? And I'd say there's two ways. One is subjective, in the sense that we can just say, like, literally a 3 is weak, a 6 is moderate, a 10 is strong, and then, you know, after that, very strong, etc. another way we can look at it is we can literally interpret these numbers as real log odds, and we can work them out for different situations. So here's like a thing that I've been thinking of. It's kind of like the box diagram method. So if we look at here, the two terms we have is, and this is kind of like a nice little odds thing, because right here we have, this is like nice and symmetric in this form. So here we have H and not H. So hypothesis is true, hypothesis is not true. We have it on the top and bottom. And here we have it as a condition. So basically we're saying data given our hypothesis and data given our hypothesis is not true. And we want this ratio. So we can kind of say, all right, well, if this box is where my hypothesis is true. So to make this really concrete, imagine this is like, for example, all the people who are treated for some disease, or it could be all the people who are committing fraud at our company, or it could be many different things. We could say, okay, this is all the things where the hypothesis is true, and this is the amount of cases that would generate the data D. So for example, like this is all the you know, fraudsters who have, I don't know, more than, this is having more than 10 accounts or something, having more than 10 registered accounts to the same IP address, maybe. That would be like maybe an indicator of fraud. So we'll say, okay, these are people, and 40% of them do it. And then we'd say, okay, here are people who are not fraudsters and 20% of them do it. The ratio of these two shaded regions is 2 to 1. And so in that case, the signal has more than 10 accounts on the same IP address would be 3 decibels of evidence. And if these signals were independent, which they may not be, but if they were independent, it would be exact to just add up these evidential decibels. So just to give you a feeling, this is kind of...
we have a question.
Oh, thank you, Jack.
Which is that, what about considering this as a fuzzy linguistic labeling model, i.e. replacing the decibel scale with weak, significant, confident, almost certain? A weak won't really impact a confident. I guess what the question is asking is to defend the use of sort of the decibel scale versus some other sort of implicit human labeling for the...
Yeah, that's a super, super good question. And so I would say there's probably like, I would say three reasons why we'd want to do this. So I would say reason number one is that in the case of reasoning, we just get something that's clever, like Benjamin Franklin's decision system. So if we just take the system as it is and just use these like nice whole numbers, we get a system which is almost identical to Benjamin Franklin's decision-making system. So it's kind of like, it's a generalization of it in that it gives us a little bit more power, but without hopefully adding much at all more complexity. The next thing is we can kind of say, well, again, with trying to bridge this gap between like quantifying evidence and pure subjectivism, that's what the great thing about this sort of decibel scale gives us, is it's kind of like almost like a map that takes us between very, very kind of folk subjective judgments, strong, moderate, so weak, moderate, strong, and gives us this kind of map to transport that into a kind of more quantitative setting. And I would say the third reason is because once you really understand this, it allows you to create very interpretable models through expert solicitation. So I'm going to claim that basically, like in a lot of situations, you could literally just sit down, like you as a statistician or a data scientist could sit down with an expert and create a decibel system for some particular decision making, and then that could be like immediately put into like this is basically a kind of folk logistic regression. It's not even folk logistic regression, it's a regular logistic regression, just not shown in the same terms you would normally expect. So it allows you to kind of bridge this gap between the very algorithmic heavy side of machine learning, which is normally what you see, and the kind of day-to-day decision making. So that would be the three sort of reasons I would say that are like the strongest. And also thinking in this way just lets you, I would say, understand a little bit better what Bayesianism even is. So the fourth reason would be as a kind of pedagogical tool for bringing across the intuition of Bayesianism. So you kind of might say, well, this thing here is just like, all you've done is identify what the hypotheses are, what the prior is, and given me like a systematic way to synthesize my evidence. And I would say yes, but that's kind of the whole point of Bayesianism. And it makes you realize that if I'm defining the priors and likelihoods, it's very subjective exactly what form they take. But what it does constrain is once I've put down my evidence and kind of my subjective judgments of that evidence, we can see now that we have a surprisingly rigorous way to then join that evidence or add that evidence together. We got a question. Sorry, Javier, do you want to ask your question verbally?
Yeah, I'm here. It's not quite a question. It's a comment. This is really a slide rule. The slide rule is a computation device that turns multiplication into addition by mapping numbers into lengths. So you get two lengths, you add them, and then you read the product of the two numbers that you mapped into the logarithms. So essentially what this is doing is the same, but for mental calculation. It helps, as you say, see it as a way of a logistic regression, but it also helps seeing it as kind of a mental slide rule or a slide rule-like mechanism for dealing with probabilities and ratios of probabilities. Because then they become, instead of ratios, they become additions and subtractions.
Yeah, absolutely, Javier. The trick is that you don't use the logarithm, use the log odds, which is the standard logistic trick. And that's what makes this diagram work here, that you have this nice, you have this very, very nice connection between probabilities, like 1 minus ratios are flipped, sorry, not ratios, odds are flipped, and then these correctly add. But what I guess what I'm trying to say is that when we add these, as logarithms, we're manipulating the odds, not the probabilities directly. And that's why we get some of the tricks. So it's kind of using two tricks. It's using a log trick, it's using the decibel trick, and it's using the odds thing into a coherent system where we have nice whole numbers. And so that's kind of the last trick, is that's the mental bit, which you absolutely correctly identified, which is that if we have this in our brains, then we can do it very quickly without even, like if you can memorize this, which is not too difficult, you can then basically go and solve any calculation very quickly. And also the thing that makes this really easy to remember is you really only need to remember this one and this one, because all the other ones are consequences of it. So for example, like 3 here is a ratio of 2. So the 10 minus 3 gives us the ratio of 5 to 1. And also for the 4, that's just 2 times 2. And so you can work out a lot of the other ones really quickly without even having to remember them. So really all you have to remember is this one and this one. And these ones are useful too.
Andy, could I push maybe just some of if you could be a bit more substantive on the applications of this in ML or AI setting?
Yeah, absolutely. So I'll just go through this like diagram section really quickly, and then I'll sort of address that. Actually, no, I'll do it now. So I would say the biggest application I would see for like the ML and AI thing is full interpretability. And so I think one of the things that we're coming up against is the fact that even the best explanation systems out there are not usable really for everyday people. So one of these stories that really affected me was by Andrew Gelman, and he was doing work on basically like neglected children. And so what they had was basically many past case files of children that had been neglected, and what interventions this particular like particular sort of what do you call, like charity organization, what they had done. And so you could kind of imagine someone just like throwing that in the pot, maybe doing some like neural nets, or maybe just even some like regression, and then throwing out a predictive model. But the problem is with something like that is it's a very sensitive situation. The choices they might make need to be understandable by judges, legally justified. So what he did was he created a simple point system. And that point system was along the lines of, there were like 5 categories. I think it was like shelter, access to food and water. There were like a number of categories. And then there was like 3 levels in each category, like medium, like, so there was 5 levels of deprivation in each category. And the idea was basically, I think he came up with a rule, which was, if you have a 5 in any category, then this needs to go immediately before a judge. Or if you have like, I think it was a 4 in 3 categories or more, then this needs to go for a judge. And, you know, he can then go back and take that rule and match it up with decisions that have been made in the past, and quantify like how well does this fit the data. But the whole point is that the thing he produced wasn't, like the analysis was still very rigorous and the work was still very, very earnest. But what he produced wasn't like a NumPy script. It was literally like this usable system, which was very simple and understandable. So I think that like the major use of this is when you're in a situation where you have a whole bunch of data, but the decisions are very sensitive. There are extraordinary reasons why these need to be ultra transparent, like why and how decisions were made. That's when you'd use a system designed on this basis. Because basically like you get this dual world where you can make something which is completely understandable by everyday people. If you just like drop the DB, it's basically like a dolly quiz. It's like a quiz you'd find in the newspaper, but it gives you a quantitative interpretation, which lets you do things like, hey, what's my log loss? Or, you know, full Bayesian model checking, stuff like that.
Rank out a back test.
Yeah, exactly. Yeah. So you could like code this up right now and you know, you could absolutely, then that would just be almost a classic machine learning model. So here we go. Here's a 2-to-1 evidence, a 4-to-1 evidence. We've got 10-to-1. So this is kind of like your evidence is getting stronger now, and especially because this becomes very rare in the like when the hypothesis isn't true. Here's like a 20 decibel case. And so this lets you work out really quickly. For example, you know, those really annoying problems you get in like introductory statistics, where you should have to like write down all this stuff. So here's the thing. If a disease, or like, yeah, let's say a disease has a rough prevalence in the population of like 1 in 1,000. Well, then our prior is 30 decibels against. I get a test and it's 99% sensitive and 1%, and the specificity is 1%, or 99%, no, 1%. Then we end up with this ratio of basically 20 dB. So we were at minus 30, we add the 20, and we get to 10, which means that after getting this pretty good test for a rare disease, your posterior probability is 10-to-1, or about 1 in 10. And that allows you to like do those sorts of calculations super quickly. Here's a important case, which is if the prevalence of your data is the same, and this is like the nice thing about these box diagrams. Intuitively, you know this, but sometimes it's good to see it again. If your data is, if there's exactly the same probability of seeing your data in both cases, this gives 0 evidence, which like intuitively is very unsurprising when presented like this, but it's just something to keep in mind that we don't often think about. Cool. So that concludes this kind of section on a Bayesian system.
If I can just get you, Andy, there's been a couple of messages coming to me about on the case study there. That was Andrew Gelman, you said?
Yeah, Andrew Gelman. I'll try and find the link. I read it a long time ago, but yeah, it's Andrew Gelman. He's got a blog. He's got a blog that's absolutely worth reading.
Cool. We might update that on the Meetup group or something.
Yeah. I'll try and find the specific article. So there are extensions of like, this is something that I've actually been thinking about, is like, I think it would be really useful to people. There is extensions to like when you need to make decisions between multiple categories. And I'm also trying to think of some really simple ways to take into account non-independence of evidence, which is one of the weakest things about this system, is that if you have like 5 experts who almost always agree, then obviously just multiplying their evidence by 5 is not really correct. And so I think what's needed is like an intuitive way, like a really simple and intuitive way to say, okay, if you have sources of evidence which are already like which almost always agree, then there's some attenuation to the evidence. So it's like some sort of like decibel like factor that you remove that kind of corrects for the fact that your evidence is not independent. And if you had any ideas on that, I'd love to hear them. Cool. So I'll just pause briefly for some more questions and to take some water, but I do definitely want to get some feedback because I think everyone's been kind of quiet today. I want to hear it. Lizzie, you're good at coming up with gotcha questions.
Hey, I already did my bit. Quit picking on me.
Thank you. I appreciate it a lot.
So I guess
Again,
I gotta ask.
Oh yeah, Paul.
Do you use this in real life for making decisions yourself?
You know what? I only just came up with it recently, but I am absolutely going to start using it, and I'm going to find out whether it like is actually useful.
I look forward to hearing your feedback.
Yeah, they'll be like, you'll meet me sometime like in a couple of months. It'll just be like these little tables like scroll all over each wall in my house. It'll be like, do I wear a hat today? Honey, 3.
Philip K. Dick and I Ching. Constantly, having to check every decision that you make.
Absolutely. In fact, yeah, I should do a challenge like you, Paul. I should do like a whole month where I cannot make any decisions without putting them into a long evidence scale.
Be a good follow-up presentation.
Yeah, I'll do that one remote from prison.
Yeah.
No, not prison. The what's the one?
Asylum.
Asylum. That's the one.
Yeah.
Awesome. So how are we doing for time? Okay, pretty good. So we've got one last section, and so I was telling you that I spent way too much time on the diagrams. Look at these beautiful diagrams. I spent way too much time on them. I even wrote a script that generates these diagrams. So you can like put in what percentages you want, and it'll just put them together. And look, if it's too small, it even puts the arrow in.
We can't see. We can't see.
Oh, sorry, Paul. I gotta share. I keep flipping in and out. I can't admit people while I'm sharing my screen, which is really annoying. So anyway, look at this. The arrow just disappears when it gets above a certain percentage. Oh, wow. Man.
Did you code this up, you're saying? Is this code?
This is like code that generates these diagrams. Wow. Okay, I know, I'm a giant nerd. So, okay, the SVD is the center of all linear methods. And I think the title of this was Linear Models in the Time of Deep Learning. So I think that linear models are incredibly important as a fundamental basis, because essentially, and this is a really, really important thing, almost always you're going to remove the linear effect and then try and like fit your model on the nonlinear part if it's a neural network. Now there's one specific exception to that, which is that modern CNNs are so large and so powerful that people don't tend to whiten their data anymore, but in almost every situation you're in, you probably should be doing some kind of whitening before you send your data into a neural network. And in that case, what you're essentially doing is like removing the linear component and then fitting your model to the nonlinear part. So understanding linear methods is really important. And this kind of really connects to like, what is structure and like, what are we even trying to do? And so you hear this thing that gets thrown around a lot, which is like manifold learning, or the manifold of natural images and whatnot. But here's a point, which is that a plane is a manifold. If you have like a 2-dimensional data set and it's squished up onto a line with some noise, that's intrinsically one-dimensional plus noise. And so you can kind of think of it as there is a manifold, which in this case happens to be a line. In fact, anytime your manifold is a line, you can deploy linear methods. So, you know, in 3 dimensions, if all your data is kind of collected onto like this flat pancake, then clearly your data is kind of 2-dimensional, but embedded in this or immersed in this 3-dimensional setting. So what we're really trying to find is like, can we get these like can we pull out these lower dimensional subspaces? And so let me just stop sharing and see if anyone needs to be let in. No, okay, great. So I'm going to show you a thing which is like blown my mind. And in fact, as I was like putting this talk together to explain this, I actually realized this. So here we go. Look at this beautiful, can we all see this beautiful diagram? This I spent like an hour on, but isn't it pretty? So here we've got the SVD, and you can see that we can basically like, we can use U, we can use V, we can truncate this, and we can do some stuff here. But here's the mind-boggling bit. If you take the SVD, is at the heart of all linear methods, and here's why. Because if you look at what each of these things is, almost any combination of these 3 symbols yields one of the well-known like statistical tools for linear data analysis. So this, like, I was literally like drawing this out, and I was like just writing this list, and I was like, oh, is there anything I forgot? And then I realized that I could just check by like being like, what possible combinations of U, sigma, and V are there? And then ask the question, does that correspond to like some kind of method? And so the answer is yes, you can go through all the interesting combinations and they all correspond to a method. And so like, what is the intuition behind this? Like, why does this even freaking happen? And why does it even work? So this is like, I was trying to explain how cool this was to Laura, and I was sort of trying to put it like, you read like about 6 different techniques or 7 different techniques in a textbook, and they seem kind of unconnected. And then at some point you realize that they're all kind of like shadows of the same fundamental concept, and that they're all kind of deeply connected in this way. And in fact, like at the center of it all is the SVD. So kind of like, why the hell is this? And I think it's the best way to kind of describe it is that if you have this like squashed pancake, so we've got like 3-dimensional, let's say a 3-dimensional space, but think, you know, 14-dimensional. Just think 3-dimensional and say 14 really loud. That's the old Jeffrey Hinton joke. If our data has some kind of like latent structure that's linear, it's going to lie in a lower dimensional manifold that is also a hyperplane. That's kind of like the linearity assumption. In fact, if we don't think that low dimensional manifold is a hyperplane, that's when we get to nonlinear methods, and we get to like, you know, trying to learn the manifold of natural images. But if we believe that that manifold, if we have some reason to believe that manifold is linear, approximately linear, we'll have like this squashed pancake immersed in this much larger space. And what the SVD is going to do is it's going to find what the V, so that's going to be the right singular vectors, are going to be the kind of major axes of this pancake. So I think this is where we get to the I should draw stuff. And I apologize because I would have liked to have like a huge amount of slides on this, but I just didn't get that chance. Okie dokie. So here we go. We've got our ambient space, and we believe our data is kind of on this squished, we believe our data is kind of on this flat pancake. And so like our data points are all around it. And this is, I'm going to say, basically 2-dimensional, but it's immersed in 3-dimensional space. So what are the singular vectors going to correspond to? They're going to be the major and minor axes of this pancake, and then also a tiny little vector sticking out here, which just tells us like, are we deviating a little bit from the surface of this pancake? And now already we know that if the SVD is like USV, then each of these dots, like the U matrix has how far to get to each dot. It says how far should you go along this axis, how far should you go along that one, and how far should you go along this one. So these three axes here are the principal axes, and they come in V. The principal components come in U. And also we can do lots of different whitening things. So for example, the diagonal elements of sigma in the SVD are going to be the lengths, essentially, or maybe the squared lengths. No, the lengths of these little kind of axes here. So if you want to whiten this data, we can just basically either just take U, or we can we can drop that scaling. And that's why when we go up here and we just drop sigma, we get zero phase component analysis, which is a variant of PCA. If we just take U, we get the classic PCA. If we take V, which is basically taking the taking these three axes here and using them for something to try and make predictions, we get a we get this thing called total least squares, and we can also do some things here where we use all three. So if we truncate sigma, which is basically saying, okay, take only, like imagine if I said, I want the best rank 2 approximation to my data. Well, then in this flat pancake, I would certainly just want to throw away this last vestigial dimension here, because almost all the information is in my two major and minor axes of this kind of pancake. This is like a pancake plus noise. So in that case, if I just truncate sigma, and I guess V and U, this is probably a better way to write it, but if I truncate them, what I get, or just kind of set the we take the three largest and set the rest to 0 in this matrix, we get the best low rank approximation, because the best low rank approximation to our pancake is these two vectors here. If we then divide by, so this plus is replace all the non-zero elements with their reciprocal, we get the ordinary least squares slash like more Penrose inverse. So basically, like, knowing the shape of this kind of like low dimensional representation, this hyperplane, which approximates our data best, is actually kind of this nexus which connects like all popular linear methods. And this is like, I really, when I put this together, it like blew my freaking mind, because it's so abstract to kind of like take this equation and just be like, okay, if I take any part of it, it turns out I get something really cool. So that's just something totally, totally mind-blowing. I'll probably have questions about it. So I'm going to stop sharing and check. Oh, Laura's looking at the stats modeling thing. Okay. Paul, were you talking?
No, I was on mute.
Weird, you're the one that came up.
Oh,
cool.
weird.
Yeah. Are there any questions about the SVD thing? Because I feel like it's quite a lot.
Given that it's the basis of these other points, why do you feel it's undertaught or underrepresented as far as linear algebra?
Yeah, super good question, man. I don't know. I honestly don't know. Like, I've never seen a presentation like this before, where like the connections between the SVD and all the other things are like made so apparent. And like, I honestly don't know. It's kind of like maybe a lot of people are not looking for like a unified view. They just want to have like these particular tools which like allow them to solve a particular problem. So I think it's like more straightforward just to like teach that tool instead of like its unification. It could be why, but yeah, I've never seen this presentation before. And in fact, if you have, or you come across it, let me know, because I'd love to know like what textbook or whatever has that. Oh, I've called this the SVD rose because it's like a compass rose, but it like goes in lots of directions.
Yeah, I mean, I've certainly been dicking around with linear algebra concepts for probably about 5 years or so, and I've never seen this sort of representation, even though I'm aware of all of the different components kind of individually. So it's, yes, it's surprising to say the least.
Yeah, it really is. And in fact, like I was just going to have a table, like a boring table. But then I realized I was like chatting over lunch with my partner about like how to lay this out in like a visually appealing way. And I think we nailed it. I want to get this on like, maybe I get this like tattooed on my butt. Along with the pancake. It's like a pancake and that. People will be like, what the hell is it? You're like, you have to be there, man. Cool beans. Okay, so I think considering it's already 7:30, we maybe won't do the bonus round. I don't know. It depends. I feel like maybe bonus round could be a whole nother talk. Really. Let me get some feelings from the audience. It's a quiet audience today. Making me worried that like I didn't explain. I fully endorse that tattoo idea. Yeah, nice. Thanks, Ben. I feel like it's been a kind of quiet group. I could maybe get a moderate intermediate. I could certainly get that as like a t-shirt. Actually, here's a good question, Jack. If I made this a poster or a sticker, would you be into it?
Would I be into it if it was a poster or a sticker?
Yeah.
I have a background of a digitally altered Mark Zuckerberg. I don't know if you really want to be taking
aesthetic advice
for me. It's a fairly niche image, but yes, maybe a poster. I can see there's a suggestion in the chat of a poster would be good. It's certainly more usable than you getting it tattooed on your body and attending. Like, how many lectures can you attend in 1 year?
That's true. And I'd have to moon everyone there every time. Okay, well, look, I think considering the kind of audience is like a little bit low energy, I might say we'll skip the bonus one. So I guess then we can do like, well, I'll talk slowly and hope that some more questions pop up. And I guess we can talk about like housekeeping. So we don't have a speaker lined up for next month. I think that the MLAI/speak should be open. So if you have wanted to speak at MLAI and you like the idea of doing it remote, definitely put in like a thing to the speaker thing. Otherwise, I'm sure I'll look through my contacts and see who might be good for like speaking remotely as well. Also, if right now, just while I've got everyone here, if there are like topics that you're kind of interested in, that would be good to throw out there because that'll give me some like direction on what to look for speakers.
It's also might be worth saying it doesn't have to be an hour. We'll take a 10-minute, 20-minute talk if you prefer to speak for a shorter amount of time.
Yeah, thanks, Jack. For sure. Cool. Yeah, so I'm getting worried here that like people weren't into my talk. So please ask me some questions. It'll make me feel better. Jack, you've already done the lion's share though. I appreciate that. Thank you. It was very kind of you.
Oh, sorry. Go ahead, Paul.
Oh no, I was just about to say that end bit was a bit over my head. So if I had questions, I'd ask.
Okay. Yeah.
Look.
Again with the clearing out the back of the closet and the mind palace. This is the problem. They're all like, none of these tidbits are like cool. They're like, oh, that's awesome. But like, where do you put it? But,
sorry to single you out, but Michael, I could see yours, Michael McGrath. I could see you're still on the call. I tried to paraphrase your question a little bit about using word labels rather than the decibel scale. Did that answer your question, or was there more thoughts you had on that?
No, we lost Michael.
Lost Michael? He's hung up.
So he's gone.
Shit, that backfired.
Oh well, yeah. But I will say, okay. Here's the thing. I will I really like the additive Bayes rule, and I honestly, I'll go and say I actually kind of wish I was taught probability as decibels instead of numbers, because like numbers and having to like have lots of weird like add and subtract like lots of kind of finicky terms and like ratios. It's like I remember the first time having to do that like question with the medical test, and it taking me ages. And I honestly think that like decibels are like the right way to talk about evidence. And I think like you'll like if for example here's actually Jack, remember your thing was like where could you use this in like stats and ML modeling? If you're doing logistic regression, I highly recommend if you standardize your data and then you report your logits in decibels, that will literally be like decibels of evidence per standard deviation, which is like really, really interpretable, because it basically says, for example, like if my logit is 3, then it basically says that one standard deviation change in this variable will take me from indifference to like small support, or like a 6 or something would be like one standard deviation change in this dimension takes me from indifferent to 4 to 1. So it becomes very easy to just read off like what a logit means in a logistic regression if you put things on this scale.
Yeah, I can certainly see the value in it. It's got kind of a good compromise between the granularity of the sort of a percentage scale that you might use or something like that, but it also doesn't sacrifice the explainability as well.
Yeah, I agree. I wish stats used this. I struggle with stats. I did not enjoy it. So maybe this would have made it a little bit easier.
Yeah, I think stats, the way stats is taught is like way more confusing than it needs to be. I found like, I'm not making this up, I found stats like really confusing when I was learning it as well. Really confusing. And I think it's just somehow about the way it's taught is like almost ass backwards.
I completely agree. I think it's taught like crazy. It doesn't make sense to me when I first learned it.
Yeah, and like literally the way I understood like p-values and frequentism and a bunch of stuff was like I learned Bayesian inference, and then I came back to it and was like, oh, now I kind of get it. So it was kind of like I had to like come all the way back to even really like intuitively understand it. Awesome. Well, I think that we should probably, it's 7:30, so we should probably start wrapping things up. Thank you so much for coming, everyone. I really, really hope you got something out of that talk. I really want feedback on all these different ideas, because I think they're all kind of raw. Like there's gems there, but they need kind of refining. And so like that refinement is like going to be your questions and like your kind of like overall like, yeah, like these things are still being developed. So if you want to yeah, if you want, I appreciate your feedback.